Math Analyzers. Let's review Chapter 8, Lessons 1 through 3 together. So just we'll stop and we'll talk about what we have reminded ourselves about so far as it goes with Pythagorean theorem and special right triangles, and then the sine, cosine, and tangent ratios that we use, right? Here we go. The Pythagorean theorem is a squared plus b squared equals c squared, where A and B are legs in a right triangle, and C is the hypotenuse. Okay, so here is my right triangle, here is my right angle, which means C is the hypotenuse, the side across from the right angle, and A and B are interchangeable with the legs because it really doesn't matter if they're the same height, if they're different heights, one is smaller than the other, whatever, that part really doesn't matter. What matters is the A and B are the legs, the longest side, the hypotenuse side, the side across from the right angle, that's got to be your C side. Okay, so that's the one that's on its own on the other side of the equal sign being squared. Okay. Pythagorean triples are special patterns where all the sides in a right triangle work out to be integers using the Pythagorean theorem. Okay, so we're just going back and referencing a squared plus b squared equals c squared again, this relationship between the sides in the right triangles, right? Examples of Pythagorean triples. So I did tell you that it would be really good for you if you memorize these. The first three really are the ones like 3, 4, 5, 5, 12, 13, and 8, 15, 17. Those really are the ones that if you're going to memorize these, those are the ones to pick. Any multiples of those are also special right triangles called Pythagorean triples. So, for example, this is actually a 3, 4, 5. Okay, 3 times 3 is 9. 4 times 3 is 12. 5 times 3 is 15. 9, 12, 15 special right triangle. So that would also work in the Pythagorean theorem. So any sort of multiples of these specific 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, and 9, 40, 41 are the other ones I mentioned in your notes. Okay. And of course, there's more, but those are so big, they're just not going to be feasible with what we're going to be looking at. Other special right triangles. So now we were focused in on the sides in lesson 1. We were talking all about the sides in lesson 1, but of course there are angles, 3 angles in fact, in right triangles. And when we're looking at these right triangles, our other special right triangles are 30, 60, 90, and 45, 45, 90. The 45, 45, 90 are, of course, the ones that are isosceles, right? These sides are congruent. They're the only isosceles right triangles that exist, okay? And it's because if you have a right triangle, you have to have a 90-degree angle, and that means that these other 2 angles have to be divided by the 90 degrees that's left, okay, in a whole triangle. So it's the only possible isosceles right triangle is a 45, 45, 90. The 30, 60, 90 also have a very wonderful relationship. So these are just very unique relationships in these right triangles. The relationships in these sides, no matter what size triangle, if it's got these angle measures, the proportions of the sides will be in this order. Okay, so in a 30, 60, 90, the sides are always in the ratio of 1, radical 3, 2. Meaning the smallest side would be your 1. The hypotenuse side, your largest side, is double that. And your long leg is 1 times radical 3. Whatever your value is of your smallest side times radical 3. And we did practice how to go back and forth depending on which length of a side we know in a 30, 60, 90 triangle. We did the same thing in 45, 45, 90 triangles. Okay, we did the same thing, but these are in a ratio of 1, 1, radical 2, right? So two of the legs, or the two legs, I guess I should say, will obviously be the same length because they're across from angles that are the same measure. And when that's the case, those sides are the same. That's an isosceles triangle right there. Okay, so that leaves the hypotenuse to be the radical 2. And that's in proportion to whatever the lengths of the sides are. So if this side is 1, you multiply 1 times radical 2 to get the length of the hypotenuse. There are 3 main trigonometric ratios that describe the proportion of the lengths of the sides of right triangles to the measure of the angles. This is true. They are sine, cosine, and tangent. Sine, cosine, and tangent. Okay, we do abbreviate sine, S-I-N, we still say sine. We do abbreviate cosine, C-O-S, we still say cosine. And we do abbreviate tangent, T-A-N, we still say tangent. Sine, cosine, and tangent are our right triangle trigonometric ratios. Okay, and again, this ratio is in proportion to, using this function with the angle in question, it's in proportion to whichever sides we're looking at, okay, in our right triangle. Because each of these covers 2 sides of the right triangle in their proportionality. So we're going to do that right here. Oh, I put a big old theta right here in the corner. Now this is our right angle right here. Here's our big old theta in the corner. Our hypotenuse is always the side across from the right angle. So the hypotenuse side, as far as labeling is concerned, is always nice and easy, right across from the right angle. The other two depend on where your angle in question is. Your opposite side is the side across from your angle in question. And your adjacent side is next to the angle in question. Okay, so if that helps you with your, if it helps you to label, do that each time. And like I said, label that hypotenuse first. I like to do opposite next because I feel like I'm really making sure this side over here is across from my angle. That will leave me the adjacent side, because that's the one that people kind of get wrong. Okay, so the sine of theta ratio is the opposite over the hypotenuse. The cosine of theta side ratio, is adjacent side. Oh, I was about to spell that wrong. Over the hypotenuse side. And the tangent of theta ratio is opposite over adjacent. And of course, we have that lovely SOHCAHTOA to remind us the ratios, right? So this is just a little saying that we've all heard and learned and used to remind us the ratios that belong together, the sides that belong with each of the ratios. So what we're going to do here is we are just going to do a little bit of practice as far as, is this a Pythagorean triple? And then we're going to, from the angle in question, we're going to state all of the sine, cosine, tangent ratios, okay, in each of these. So here we go. 8, 15, 17 is a Pythagorean triple. There is my angle in question right here. So obviously 17 is going to be my hypotenuse. It is the longest side. It is the side across from the right angle. From my angle in question, 8 is the opposite side, and 15 is the adjacent side. So when I'm being asked what's the sine theta ratio here in this triangle, it's opposite over adjacent, or 8 over 15. What's the cosine theta ratio in this right triangle? That's adjacent over hypotenuse, so it's 15 over 17. What's the tangent theta ratio in this right triangle? Opposite over adjacent, 8 over 15. Okay, that's it. That's all we're looking at. Okay. I'm going to leave you number 2 to try. Oh, those are on there. Okay, never mind. I thought that was like a messy paper, but that's just me not cleaning up my pictures. I'm going to leave you number 2 to try on your own, but how about number 3? Is this a Pythagorean triple? And the answer is no. I mean, they're not even all integers. So yeah, I mean, radical 13. Not even all integers. Here's my angle in question. This is the hypotenuse. Across from the angle in question is the 6. Next to the angle in question is the radical 13. So let's go. The sine is opposite over hypotenuse. That'd be 6 over 7. The cosine is adjacent over hypotenuse. That's radical 13 over 7. And the and the tangent is opposite over adjacent. That's 6 over radical 13. Am I allowed to leave a radical in a denominator? No. So we've got to rationalize, multiply top and bottom by radical 13. Radical 13 times radical 13 is radical 169. And of course, the square root of 16 is square root of 169 is 13. So I can just bring that out. On top over here, 6 times radical 13 is 6 radical 13. 6 and 13 are not evenly divisible by the same number, so there's my final answer. Never leave a radical in a denominator. Okay, never leave a radical in a denominator. Let me just look at what else we got. Oh, you can use your graphing calculator to do those. Round to the nearest 10,000th, 4 decimal places. Make sure your calculator is in degree mode. Okay, I know I said that a ton in the video when we were doing this, but that is super important. Make sure your graphing calculator is in degree mode. So I press mode and look, I've got degree mode, so I'm good. I could just go right in and do these ratios. Okay, type in these ratios. So there's some special ratios in there. Okay, if you come up with something weird there, how about I do the weird one, right? Second in mode, tangent of 90 gives me undefined. I'll talk about that more with you later, but essentially, you can't have the tangent of 90. You end up with a 0 in a denominator. We'll talk more about that one another time. Okay. We want to do one more time looking at a 30, 60, 90 right triangle and knowing one side, right? A 45, 45, 90 right triangle and knowing one side. One more time to just show you the chart to use. And then again, you have the answer key to these, so I'll let you give them a shot. But you've got 30, 60, 90, 30, 60, 90, x radical 3, and 2x. Let's see, the side I do know is across from 60, so it's here, which means if I'm going backwards to find my 30, right, to find my side across from 30, my short leg, I need to take 8 and divide it by radical 3, which of course means rationalizing. So I get 3 in the denominator and 8 radical 3 in the numerator. So 8 radical 3 over 3 ends up being my answer there. Multiply that by 2 to get the hypotenuse side. So 2 times 18 is 16 radical 3 over 3. Okay, that's where I would get my answers from. Same kind of deal when you got a 45, 45, 90. This one is x, and x radical 2. So in this case, I know one leg, keep sliding out of my chair. Okay, I know one leg. That means I know the other leg because it's isosceles. Those are the same length. And actually, I just take this and multiply it by radical 2. So 7 radical 2. There's the hypotenuse. Over here, last ones, find the missing lengths of sides using Pythagorean theorem. Okay, I'm actually just going to do that in my graphing calculator. So we know the hypotenuse here is 8 squared is 64 minus the 7 squared is 49. Oh, how about 49? And that's going to leave us with 15. That means this side is radical 15. And no, radical 15 cannot simplify any further. Here I need this side first, and then I can know this side. So I'll just call them x and y, right? There's your hypotenuse. So 17 squared is 289 minus 9 squared is 81. Let's see what's left over for that middle. Okay, so this needs to be radical 208. 208 can evenly divide by 4 at the least. What's left? Oh, another 4. So 208 divided by 16. There we go. So this would be 4 radical 13 on this side. Now this one will be a little bit more complicated as far as our Pythagorean theorem, right? Because I'm going to have to square 4 radical 13. Okay. Now this is my hypotenuse. So 16 squared is 256 minus 4 radical 13 squared. Well, actually, let's just throw it in here and square it. Just like that. Whatever. Radical 13 times radical 13 is radical 169, right? And 169, square root of 169 is 13. And then you multiply that by 4 squared, which is 16. Oh, it's like just going back to getting that 208 again. Makes sense, right? Because that was the square root of 208. See how that worked, right? So this was really 256 minus 208. So y equals radical 48. 48 is also evenly divisible by 16. And when you divide it by 16, you get 3 as a leftover. So y equals 4 radical 3. This little guy right here. Cool, huh? There you go. So just a couple trig ratios for you to do. And question number 2. You're all set. Getting ready for your quiz. Hey, good luck. Nice little review there of what we've done so far. Now we're going to actually use our trig ratios to find missing lengths of sides in right triangles and find missing angles of right triangles and then solve real life scenarios. So we'll be using those. Oh, and trig versus Pythagorean theorem, which one to use when, right? Since now we've got 2 of these back in our purview. So yeah, we're good. Guys, I'll be seeing you soon. Good luck on your chapter 8 quiz. Bye.